In this video, we'll look at and derive the gradient of the loss function with respect to the output layer of a neural network. Now, in our derivation of stochastic gradient descent for neural network training, we are now at this part where we need a procedure for computing the parameter gradients. This is actually, so making the whole derivation of the gradients is actually a complicated step. So we'll take more than one video to make the full derivation. And in this video, we'll first look at deriving the gradients of the loss function at the output of the neural network. All right. So we'll compute the partial derivatives, and then what we'll do is that we'll combine the partial derivatives with respect to all output units into a vector form, so to get an actual gradient. Now, this is our loss function here, the negative log likelihood for the true target y. And now we're interested in what is the partial derivative with respect to the Cth output. Okay, so in this illustration here, the true class might be this neuron, and now we're looking at the partial derivative with respect to the output of the neuron, its activation. So this is illustrated by orange here on the upper part of the circle. And this neuron C might be any of the output neuron. It could be the first one, which would be if this was the label, it would be the incorrect one, or it could be the last one, which would be the correct one in this made-up example. All right. So taking the partial derivative of minus the log simply gives us -1 divided by the quantity question, f of x y. So that's because the derivative of the log is 1 over the input of the log. But now notice that this here, fx of y, the yth output, might be a different output than the cth output. So actually this might be a constant if c is not equal to y. So for this reason, we also multiply by 1 the indicator function that looks at whether y is equal to c and outputs 1 if y is equal to c, and otherwise it outputs 0. So we'll get a partial derivative of 0 if y is not c, and otherwise this is going to be 1, so we'll get a partial derivative of 1 over f of x of y. And now if we put this into vector form to get the gradient, so the full gradient of this loss function with respect to all output units, then we notice that we have -1 divided by f of x of y, no matter which output neuron we're looking at, no matter what's the value of c. And the only thing that changes between different values of c is whether we have a 1 here or a 0, whether the indicator function outputs 1 or 0. So then we can factor this out and get instead write this into vector form by constructing a vector which contains whether the indicator function before c equals 0, c equals 1, and so on up to c equals capital C minus 1. So I'll just assume at this point that I'm indexing the labels from 0 to the number of classes -1. And so this vector, I actually noted E of y. We call it the 1 hot vector, or 1 out of C vector. So it's a vector that has a bunch of zeros except at a position, and the position in question here is y. So at the position where we have y equals to its actual value, we'll get a 1, and otherwise it's going to be 0 elsewhere. Okay, so our gradient of the output is going to be minus the 1 hot vector for y divided by f of x of y. Now let's look at what's the gradient but for the pre-activation at the output layer. So now we want the partial derivative of the loss function with respect to the cth pre-activation at the output layer. So that's al plus 1 of x, and then the cth element of that vector. Now we'll look at the derivation in a second, but it turns out it has a very simple form. It's just minus whether c is the true target or not, minus what's the probability that our neural network has assigned to class C. So what's the cth output at the output layer. That's actually a very simple form. If we want to write it into a vector form to get the gradient, well, this term in vector form would become the one-hot vector, and then this term would just be would become the vector of probabilities, so the output vector f bold of x. Okay, so this is actually a gradient for the pre-activation, which is actually very, very simple mathematically. Now we'll look at the derivation of this partial derivative. I like doing this derivation because it's not necessarily, the result is simple, but getting there is not as simple, and it's we'll go through a bunch of mathematical steps that are useful in general for understanding and working with neural networks. Okay, so what we're interested in is computing this here. Now let's first do the derivative with respect to minus log. So let's pass the derivative through minus log. So it means that we will get minus 1 divided by f of xy. So that's the derivative of minus log of something. And now using the chain rule, all we'll have left to do is to multiply by the partial derivative of f of xy with respect to our pre-activation. Okay, so that's just the application of the chain rule. Now let's replace f of xy by what it actually corresponds to. It's the softmax applied on the pre-activation vector, and we just look at the yth element of that vector. And let's actually replace softmax with its definition. We remember that softmax is the exponentiated pre-activations, and if we look at the yth element, then we have the yth pre-activation, normalized by dividing by, for all possible classes, C prime, so I'm using C prime here as my index for summing over all classes, of the exponentiated pre-activations for all output units, for all values of C prime. So now we have this partial derivative here to do. So this is we have the derivative to do for a ratio of two function, and now we remember that the partial derivative of a ratio of two function with respect to x is the partial derivative of g of x with respect to x times 1 over h of x minus g of x divided by h of x squared, so the numerator divided by the denominator but squared, times the partial derivative with respect to h of x. Okay, so this is a fairly simple fact about the partial derivative with respect to a ratio. So we'll, in our case, g of x would be the numerator here, h of x would be the denominator here, and x would actually be the pre-activation for the CF output unit. So here I'm just replacing, I'm using this formula here, and so replacing the whole partial derivative by this term here, where I'm replaced g of x, h of x, and x by the actual term. And so now we just have to do this partial derivative here and this partial derivative here. All right, well, the partial derivative of the exponentiated yth pre-activation with respect to the cth pre-activation, it's going to be 0 if y is not equal to c, and otherwise the partial derivative of the exponential function is the exponential function, so we'd get the exponential of the yth pre-activation, which is exactly this term here. Now, if we do the partial derivative with respect to the cf output of the sum over all outputs of the exponentiated pre-activation, so we see we take the exponential of all the C prime pre-activations. Well, if C prime is not C in this sum, then we're doing the derivative with respect to a constant, so the term is 0. And otherwise, for C prime equal to C, well, then we have the derivative of the exponential, which is the exponential. Okay, so the partial derivative of this whole sum reduces to just the exponential of the CF pre-activation. Okay, because it's the only term that's that depends on the pre-activation, the CF pre-activation. And so the other thing that I've done is that I've taken this part here, which is squared, and I just wrote that as the denominator times itself. So I can actually separate that into a first fraction here, which takes essentially, so let me remove some ink, which takes that with 1 times the denominator. And then this other term is just, we'll use the other denominator, the other part of the squared here. Now, let's use again the definition of softmax. We actually notice that this here is the yth element of the softmax on the pre-activation vector. Same thing can be said for this term here. And now this term is actually not the yth, but the cth element of the softmax of the pre-activation. So I have the cth here. And now again, we realize that, well, the softmax of the pre-activation is just the output, so the activation of the output layer. So that's f of x. So I can replace the softmax by f of x here, here, and here. And now we notice that we're multiplying in front by -1 over f of xy. I have f of xy here, f of xy here. So I can actually cancel that with both these factors. And so this gives me indeed what's left, which is minus the indicator function of whether y is equal to c minus f of x c. So the cth output value at the output layer. Okay, so that's how you can derive the partial derivative of the loss function with respect to the pre-activation for any output neuron C. And we see how that actually reduces by reusing the definition of the softmax, actually reduces into an expression that only depends on the output activation. So we get a very simple expression.